Hello everyone and welcome to my new video. In this video, I'm going to show you how you can use Optuna to tune hyperparameters of a neural network. So it's a difficult task to tune a neural network. Most of the things there to come by intuition or by some small experiments. So you can make some small experiments if you have a large data set and the neural network is going to take it's taking a lot of time. It's not very straightforward. So we will be using Optuna today, and we also need some kind of dataset to start with. So one of the dataset that is in my mind is one of the Kaggle competitions going on right now. It's called Mechanism of Action Prediction. In which, based on drug activity, in which you classify drugs based on their biological activity. So we don't have to go through the details because it's just an example data set that we will be using today. So we have a file with training features and it's a tabular data set. So it seems like first three columns are categorical, except the very first one, which is probably the ID column, and everything else is just numerical. So the way I'm approaching this problem is not the ideal approach, obviously. So this is only to show you how you can use Optuna to tune your neural network. And then you have some targets. So you see, like, there are many different targets, 207 targets for each ID that you have. So the first thing that we do when we look at this data set, it's tabular. So it should take one vector for all the features and one vector for all the outputs for each sample. So the first thing that you need to do is to start creating some kind of data set class. Yeah, we will be using PyTorch. So you start creating some kind of dataset class, and let me make it compact today. So I'm just going to be using two files, and one of them is utils.py, which will consist of all the utils. So let's import some stuff, or we don't even need to import anything right now. So let's just get started, and then we can start with tuning, but we need these small things first. So we define a class and it's called mechanisms of action. So I will say MOA dataset. Let's say this is my class, and then inside this we have an init function. What is this init function going to take? So this is where everything becomes a little bit important. So it should have the targets, and it should have the features. So let's say self and features, comma, targets. So here the features are, in this data set we have different kinds of features, right? So I think there are more than 500 features. Let's just check. 876 columns, so 875 features. And then we say self.features is features, and self.targets is targets. Now here both features and targets are numpy array, and then we say then we define a get item function, self, and we also define one more function called the len. So, and here you can just return. So if features and targets are numpy arrays, so you can have self dot features dot shape 0 or self dot targets dot shape 0, whatever you want. And here we can now return an item, so given by an index. So item, I'm going to increase the size of this a little bit for you and hide this one. Okay, so item. So item is return a dictionary with X and Y, let's say. So X is your torch tensor, and now we need to import torch. Okay, So X is your tensor, and let's see, torch.tensor, which will take self.features, then all the features for a given item index, and the D type of this will be torch.float, because these are float features. And similarly, you have Y, which is targets. Y, self.targets. So don't worry about this complaining. I still have to fix some stuff, but this works. So now what do we have? We got our dataset object, and we have an X and Y, and now we want to get started with reading this. So let's make one more file and call it train.py. I still need to download the dataset, so let me do that in the background. So I have downloaded the dataset, and all the data is in input folder, and you can also see the features. Okay, let's not see the features, it's huge. And let's create one more folder called source and put all our code in there. Did we get it? Yeah. So all this can be moved to the source folder. Okay. So now we have a training file, and in training file, what we want to do is we want to read the data. So we need to create a function in which we read the data. We possibly we split it. So splitting is something that I'm not showing you here today, because I've shown you a lot of times. So you can obviously do that on your own. So let's import a few things. Import torch, import pandas as PD, and let's also import numpy, or maybe not, and then let's select a device. We will be training our models on GPU today, epochs. So it doesn't matter how many epochs we choose, because we are tuning it. And let's say we have one function called run training. Now in all my previous videos, we have seen that like we always divide it into folds, and then we take it according to the fold. But instead we will be doing something different here. We won't be dividing into folds now. Before the training, we will just divide it, or maybe we can. Okay, let's just divide it into folds, and it makes our life much easier. So that's also the first thing that we should do. So yeah, let's not do it in a wrong manner. So create folds.py. And here we can create our folds. So let's import pandas as PD. And now the problem is, okay, let's start with our main function. If name okay, then we read the CSV file, which is our train features.csv. So input train underscore features.csv. So we have to do that, and then we create a new column called kfold and assign -1. And you can obviously do some randomization. So it's not a requirement how you do it, if in the end you achieve some result. So I just like to do it this way, and then reset the index, and then drop the index. And your target column is targets is everything except the signal ID. So here it's not correct. So your you have to take the CSV with the targets in it. So train targets scored .csv, and then you drop the column called SIG_ID, which is the ID column, and axis is 1 dot values. So this becomes all your targets. Now the interesting part here is it's a multi-label classification problem, and for multi-label classification problem, if you want to do stratification, it comes out of the box from a library that you can use. It's called iterstrat. So from iterstrat.ml stratifiers, import multi-label. Why is it not suggesting me anything? Okay, multi-label stratified k-fold. Okay, so we got all these things. Saying something is wrong. Unused input. Okay, yeah, because we haven't used it yet. And then you can do first you initialize this multi-label stratified k-fold is your multi-label. Yeah, it should be suggesting. I don't know why it's not suggesting me. Stratified k-fold and then n splits, whatever the number of splits you want. So let's say we want 5 splits. So for fold, comma, training, comma val, in enumerate, it's like scikit-learn stratified k-fold. So mskf dot split, and then you have x is your data frame and y is your targets. So that's all you need to do, and then you loop inside here. So you can do df.lock val comma k-fold is equal to the fold number, and save this data frame in the end to CSV input / train targets underscore folds dot CSV, and don't save the index. Okay, so this is our file to split the data, and this is obviously not required for this video, but it's there. So let's go to the source folder. So today I'm using my Dell machine with a Quadro 5000 GPU, and now I run python create folds.csv, but first I need to activate the environment. Python create folds.csv, and it has created the folds for me. So if I have to look, I can go and look at the file, but we don't need to do that. And I hope it's correct. It looks correct. It doesn't seem like there is any kind of mistake. So this is validation. So we are always taking validation. This you can skip if you want. Okay, that's fine. Looks good. And now we go to our training code. So now we were defining this run training function. So that takes a fold. Now the fold is the information that we have. And it also takes a few more arguments that we will come to later. So now let's say, what is the data frame? pd.read CSV input / train underscore features.csv. So we got the train features. Now the training, now the features here, they also consist of these categorical columns. And for the sake of like this video, what I'm going to do is I'm going to drop those columns. So our data frame will become def.drop. You can use them if you want, but you have to one-hot encode them. So I'm just saving time. cp underscore dose, and the third column was cp time dose and cp type. So that was the first column. cp type, cp time, cp dose. Okay, cp underscore type, I will just keep it here. cp underscore type. time and dose. Access is 1. Okay, so we have our data frame. We've clicked this in the run training function, and now we have all the features that we need to train the model. So let's also add targets, scored targets, or just call it scored df, target df. Targets data frame is pd.read_csv. Then you have input / train underscore targets underscore folds, was it? Yeah, .csv. Okay, so we got our training features, we got our targets, and now we have like this is like the folds. It also has a folds information. So now we can take or maybe we can just call it folds to make it easy, and folds have targets, or whatever you want to call it. So targets df, and then we generate a new data frame, full data frame, let's say, which is targets underscore df. No, let's just create the features. So features is df.drop sig underscore id access equal to 1 dot columns. So except the sig id column, everything else is your. Instead of feature, we can say feature columns. And then we also have target columns. Okay, so here it will be targets underscore df, and then what you do is you're going to merge these data frames. So df is df.merge targets underscore df on the sig id column, and we will do a left join. How is left? So I think we got some things, and we can say we can try to run it. If okay, run training, fold is 0. It doesn't matter, but it's required, so that's why I put it there. And let's clear this thing. Python train.py. Is something happening? Well, probably is happening, but we don't know anything. You're trying to merge on object in 64 columns. Okay, so there is something definitely wrong, and let me take a look. So we made a big mistake here. We didn't add the comma, and that is a very big mistake. So otherwise it was giving absurd results. So we need to train that. We need to create folds again. It shouldn't take time. And then let's also check the values. So the values seem okay. So like in the end you see 3, 4, 2, 1. And now go back here to our training code, and here target columns is not just, we don't have to just drop sig id, but we also need to drop the k fold column. Okay, so then you merge on this and it should work now. Let's see. So now it should work. Hopefully it does. Yeah, okay, so it's working. So you have sig id and you have all the different kinds of features and all kinds of targets, and you have the k-fold column too. So now the fun begins, the fun part. So where we will be designing the neural network and everything else. So but before that, let's also split the data, because it's nice to just do it now and then we go into the neural network. So now you have a train df, which is your df, and then df.k fold is not equal to fold, and then we also reset the index. Index drop equal to true. So this is what we have now, and similarly we also have a valid df, and only difference is this is same as fold. Okay. So we got train df, we got valid df, and but for our data loader we need in the format of numpy arrays. So I will just say xtrain is train underscore df, and then features dot to underscore numpy. So this is my xtrain and my ytrain, and ytrain is train df target columns. That's what I feature columns, sorry, it should be feature columns, and this one should be target columns. And similarly we have x valid and y valid, and all those are very important. You have to do that, and this will take valid df and valid df, and everything else remains the same. And now what we can do is we can also import the utils file that we have created here, utils, and now we can create our data loaders. So train dataset will be utils dot more dataset. So it takes features and targets. So let me just copy them, put them here. Features is my xtrain, targets is my ytrain, and similarly I have a valid dataset. Features is x valid and y valid. Now we have imported torch. Yeah, we have, and so we can also create our data loaders. So train loader will be torch dot utils dot data loader, and here you will have train dataset and batch size. So this is, since this is tabular, it can handle large batch sizes, and number workers, let's say 8. And similarly we have a valid loader which takes valid dataset instead, and everything else I can keep the same. I don't care much about that. And you can also probably include shuffle equal to true, probably, why not? So now all this should work, and we can move to the next step. Okay, so no errors. So now we go back to our utils, and quickly we will create a engine class to train and evaluate our model. So let's see, we are in utils, and here we can create the engine class. So engine class is also, it's the same thing that you have been looking in if you're looking at my videos. So you have seen me build engine so many times, but I'm going to do it anyways. So class engine, and then we define the init function, which takes self, model, optimizer, device. It doesn't take the scheduler because let's not use a scheduler which we need for like inside every batch, but we only use the one after epoch. So self.model is model, and self.device is my device. We don't even need the device because okay, let's do that. Is device, and self.optimizer is optimizer. Okay, so we got the init function, and then we need some kind of loss function. So targets, outputs, and what is it returning? It's returning BCE with logit loss, let's say, and dot BCE. So we have to import NN from torch.nn, import NN, or import torch.nn as NN. So we got this part, and then BCE with logit loss. And here we have outputs, comma, targets. Okay, one thing in this function, I'm not using self, so it's a static method limited to this class, but it's yeah, it is static. It doesn't have it's not using anything else from the class. BCE with logit loss. Yeah, okay. And now we have our train function, which takes the training data loader. So let's say it's just let's just call it data loader. And here what we do, we put the model in train mode. We have some kind of final loss. So here they are using MSE loss or variation of MSE loss. I think column wise MSE. I don't remember, but let's say we are using MSE loss too. Or well, we are using BCE with logit loss for this video. Sorry. So for data in data loader, self.optimizer dot zero grad. So use zero grad optimizer, and then your inputs are data x, and you send it to self.device. And similarly, you have targets, which is data y, self.device. So you got inputs, you got your targets, now you have outputs, and that comes from the model inputs, right? So it should be self.model. So we have targets, we have outputs, and now we can calculate the loss. So loss is self.loss function, and we did opposite, so we need to include the targets first and then outputs. Okay, and then we do backward, loss.backward, self.optimizer.step, and that's all. And final loss, we just add loss.item. And in the end, when we are returning, so we just return final underscore loss divided by the length of data loader. Okay, so this becomes our training function. Simple and easy, right? And similarly, we have evaluate function, which is nothing but just a copy of this eval, and we don't need optimizer zero grad, we don't need loss backward, optimizer step. Everything else remains the same, right? Let's just spell it nicely, correctly. So we got a training function, we got an evaluation function, and now we need to build the model itself. So what we are going to do is we are going to build a model with some parameters, and let's try. So class model and dot module. Then we define an init function, and in here init function is going to take a few more things than you see usually. So let's say it takes number of features. What are the number of features in the data set that you have? Number of targets. Okay, and it takes a few more things, and this is where the optimization part begins. So few more things include hidden size, number of layers, hidden size, and maybe dropout. Okay, I hope you can see everything. Okay, okay, my auto formatter says it's fine, so I will just change it to n features and targets, number features, num targets, num and layers. So now it fits. Okay, so when we say super init, now we can write our something like we can define a list, layers, what layers you want. So for underscore in range and layers, so the number of layers, you just have to append to this list. So if the length of layers is 0, layers dot append, and then dot, let's say we start with a linear layer, and features, and hidden size. And similarly we can keep appending more layers, but first let's so this is like one of the layers. So we have a batch normalization if we want one dimensional, and this is hidden size here. Okay, so yeah, appended this, you have this, and you can also append layers dot append dropout, which is the same as the dropout argument. I mean the value comes from the dropout argument. Okay, and layers dot append and then dot some kind of activation, relieve activation, let's say. And if the layers, if we don't have anything in layers, we do this because we need to start from n features, but otherwise we start with hidden size. So let's add all that, and instead of n features, this will be hidden size. And you can also modify it, so you can have different kinds of variations of layers that you want. And then in the end, we also append some outputs, layers dot append and dot linear, and here we have the input will be hidden size and output will be n targets. So we got everything. Self dot model. So now you have to design a model using all these layers that you have appended. So you can do nn dot sequential and star asterisk layers. So you have designed a sequential models using layers in a list, and def forward self comma x or you can just do return self.model x. Awesome, we are almost done. So we have our model, we got our engine, we have dataset, and now we go back to our training file. So when we go back to our training file, we can add the engine and the models and everything else and see what happens. So let's say my model is utils dot model, and since it's not suggesting me, I have to copy paste stuff. So n features and targets. Okay. So we got this, and we have n features and layers, hidden size, dropout. So let's say n features is xtrain dot shape 0. That's what sorry, 1. So that's the number of features I have, and n target is ytrain dot shape 1, and layers is 2, hidden size is I don't know, 128, dropout is 0.3. So this will fetch me a model depending on the parameters that I have supplied. And now we send the model to device, and we have optimizer, which is let's use Atom optimizer. So we will also talk about this in this video a little bit, how you can tune this. Model.parameters, comma comma learning rate, LR is 0.001, let's say. And I'm not adding any scheduler. If you want, you can add it. I think the video is going to be a bit longer. So utils dot engine, and here you have model optimizer, and what else did we have? It was model. We have model. We have device, obviously, and device is device. Okay, so we got everything, and let's say our best loss is infinity. I think we imported numpy. No, we didn't import numpy as np. So let's say our best loss is infinite. We don't even need that, but anyways. So early stopping iter, let's say we wait for 10 iterations to stop, and early stopping counter is 0. So what we do for epoch and epochs, we call the training part. So training part is also very easy. So your train loss will be returned by engine.train, and that will take train data loader. I hope we did that, or it's called train loader. So train loader. And similarly, we have valid loss, that will be returned by valid loader and engine.evaluate. These are the functions that you can reuse in almost any kind of problem that you want. And now what we can do is we can probably print something. So let's print I don't know, fold epoch then let's print train loss, valid loss. So just to keep track and see if everything is working fine. And if valid loss is less than best loss, then best loss is valid underscore loss. And let's add one more parameter because you would like to save the good models, right? So save underscore model equal to false. So if you tell it to save the model, then it's going to save the model. So, and for saving the model, you just check if save model, then you save the model. Torch.save model.state underscore dict, comma model underscore whatever the fold is. So fold dot bin, model underscore fold dot bin. So if the save model parameter is true, then it's going to save the model. Okay. Else, and if valid loss is not less than best loss, then early stopping counter plus equal to 1. And if my, so this is my poor man's early stopping counter is greater than early stopping, then break the loop. Early stopping iter, yeah. So if we are not improving for 10 iterations, then we stop. Okay, so now everything is done and you should be able to train this model. Let's see if we have epochs. Epochs is there, and let's make it 100. I don't want to it to blow up. So let's see if it trains. Okay, yeah, obviously, and that's what the error was, and it should be range. And training something in the first time, it's, yeah, you have to be very lucky. And then we see if it's training. Okay, so it does seem to be doing, and we are quite lucky. So you can see like the training loss and validation loss. The validation loss is also decreasing, and everything is looking nice. So you can let it train if you want, but that's not why we are here for. We are here to tune it. So let's see. And yeah, it reached some kind of good loss too. So I don't know what it was because I'm not printing that. But anyways, now the fun part, which is not much fun anymore. So now what we do is we design a optimization function, or an we design an objective function. Sorry, not optimization. So first of all, what we are going to do is we are going to import Optuna. Okay, and now we write a objective function. So this objective function, when you're writing an objective function, it should take an argument called trial. So def objective, and it should take a argument called trial. And now here you define a dictionary called params. So which is a dictionary, and it says so every time this trial is called, these params are created. So here you have number of layers. Let's say we are tuning for number of layers, and the trials come from Optuna. So if you go to Optuna documentation, the Optuna.trial, here you will see what you can try to suggest. So you can have suggest categorical. Okay, let's not click on that. So you can have suggest categorical, you can suggest a discrete uniform, suggest some kind of float value, int, log uniform, or uniform distribution, and I think that's all you need to tune anything you want. So trial, why am I writing it trail all the time? Trial.suggest underscore int, and what is the name of the parameter? So usually this is same as the name that you have provided in the key. You can have a different name if you want. And number of layer can be anywhere between 1 and 7. And so this is where you define the kind of the grid that you want, but it's not grid search. And hidden underscore size, trial dot suggest int, hidden underscore size, and here you can have the hidden size what you want, like 162048 maybe. And you can then we had like an argument for dropout in the neural network class, so we can also add dropout trial.suggest. So now we can take it from a uniform distribution, dropout, comma, let's say dropout is anywhere between 0.1 to 0.7. And learning rate, let's say we also want to tune the learning rate, because why not, we can. Trial.suggest underscore uniform learning underscore rate. Okay, let's not do suggest uniform, but instead we can do suggest log uniform learning rate, and from 1e minus 6 to 1e minus 3. That sounds good. And we create a list called all losses. So all losses will consist of all losses from different folds, and I say for f underscore for fold in range 5, because we have 5 folds. Run the training, and also the training should return something, and this is something that we didn't do, and we should have done that. Return best underscore loss, and that's it. So we are returning the best loss. We have all the losses, and now what you do here is let's say there is a something like a temporary loss, run underscore training, and you run the training with a given fold, and you set save model to false, because you don't want to save the model when it's tuning the parameters. And all losses dot append temp loss, and in the end it will return the mean loss. So return np.mean of all underscore losses. But now one thing, where did we use params? We didn't even use params, right? We have to use it. So let's add another argument here, params, and now we modify our training function. So we go to training function and add another argument, params, and here now we change stuff. So params will, everything here will come from the dictionary. So this will be num layers, and similarly you have I think the name was hidden size. So you have params hidden size, and then you have params dropout. Was there anything else? Learning rate, yes. So here params learning rate, and now you can start tuning with Optuna. Such cool, man. And it's not so much work. Designing the neural network is much more work, right? So you create a study. It's called study, so you can have any name you want. So Optuna dot create study, and here you create you define a direction, and in this case we will be minimizing the loss. Minimize. or it can be maximized if you're returning a UC or something like that. And study dot optimize partial objective. So we also need to create a partial objective, or we don't need to create that. Probably not. Objective, because I was thinking about something else. We don't have any other parameters except trial here, so we don't need to create any kind of partial function. So we have objective and trials. Let's say we run it for 20 trials, and then you can print some stuff, best trial, and print the information about the best trial. So you can use trial, let's say trial underscore is study dot best trial. Okay, and you can print the values of the trial dot values, trial underscore dot values. And you can also print the best parameters. So we can just do that and say because we want to know the best parameters, right? Trial underscore dot best underscore dot params. So these are your best parameters. So now if you want to train the neural network from scratch and then save the model using the best parameters, so you have to do that in the end if you're not saving for all the runs, and you don't have to save for all the runs. So I will say for J in range 5, score is run underscore training. So here we had the full number, and params will be best params or trial dot underscore dot params, and save underscore model equal to true. So your model will be saved only once with the best parameters available. Scores is plus equal to SCR. And then in the end you can print what kind of out of fold score you got. So scores divided by 5. Awesome. Now we have to see if it actually works. Okay, let's clear this thing and just run the training file. So you see it is working, but that's like the very first fold. So it's doing something. It's also taking a little bit of time than the last time, but let it go on and see what happens. So seems to be working quite okay, I think. I will let it run and come back to you. So when it's running, you will also see like after all the 5 folds. So now it has finished one trial 0, and it says it finished with value of 0.08. So you see like the loss is very high, but also to make it a little bit faster, I changed some stuff. So you see it shows one layer, hidden size was 67, dropout was 0.57, learning rate was 5.59 into 10 to the power minus 5, and this is currently the best trial. So after every trial it's going to print this information, and so let it continue running, and maybe you will find very good loss. I did. So what else you can do is you can also create a function that chooses the optimizer for you, and based on a string argument. So that can be added as trial.suggest categorical. So this is just an extra information that I'm telling you, so you can do all different kinds of stuff, and that makes like Optuna very simple and easy to use. And go try it, try building a neural network from scratch, and then try to find the optimal number of layers and hidden size and dropout and learning rate and whatnot. And you can also like choose hidden states for each and every layer. So the more choices you have, the more time is going to take to find optimal parameters. But that's something that you already know. And I hope you liked this video. If there was something that you didn't understand, or if there was something that where somewhere I made a mistake, please let me know in comments. And if you do like the video, do click on the like button and do subscribe and share it with your friends. And see you next time. Bye.